Thanks for tuning into my video. I'm Adam Kashlak from the University of Alberta, and today I'll be talking about analytic permutation testing via the Kinshin inequality, or the permutationless permutation test. So this is joint work with two wonderful co-authors, the first being Sergei Marishnichenko from the University of Alberta. The second is Susanna Spector from the Sheridan College Institute of Technology and Advanced Learning. What we have here is this data called the Berkeley Growth Curve dataset, and this is available on R in the FDA package. And it has the heights from ages 1 to 18 measured of boys and girls. If we were to look at age 10, now we have two univariate samples. And we can do a comparison of the means using a two-sample t-test. But what if we wanted to do a two-sample test for entire curves, that is, the entire growth of the children from ages 1 to 18, to figure out if boys and girls grow differently throughout the first 18 years of their life? Well, we can do that. There's a package in R called FD-ANOVA, and this package will effectively do a one-way ANOVA test on functional data. Let's say we wanted to compare k-samples, but we want to compare not so much the functional means, but the covariant operators. Well, there was a 2017 paper by Kabasi et al., and this one actually approached this problem, and what they did was they used a permutation test. So they wanted to compare k different samples to each other. In this case, they were looking at mice running on wheels. It's a pretty interesting data set, so I would check out that paper if you want to know more. But the idea is that they wanted to work outside of the Hilbert space setting, and they wanted to do a k-sample test. That leads to the question, what is a permutation test? The permutation test is a type of exact non-parametric test. I no longer have to assume normality or any other distribution. In this case, all I have to do is assume that under the null hypothesis that my test statistic is invariant to any permutation. And what I'm doing now is I'm no longer computing a p-value based on the distribution of the data. I'm computing a p-value conditional on the data. If we have even a moderately large sample size, 2n factorial, which is the cardinality of the symmetric group on 2n elements, is really, really large. So we're never going to be able to exhaustively go through every single permutation to compute this p-value exactly. So instead, what researchers do is they simulate, well, what would happen if we wanted to do such a k-sample test for covariance operators? And what if we had other experimental factors in our design, such as a blocking factor? And now what if we want to correct for multiple testing as well, because we're doing k-choose two different pairwise comparisons? I guess we're going to need a bigger permutation test, a really big permutation test. That leads to the question of, can I do a permutation test without ever actually randomly generating any permutation? So this takes us back to 1923 and the original Kinshin inequality. Here we have 2n Rademacher random variables, which are going to be random signs. They take the value of +1 or -1 with equal probability. For any fixed vector, x1 through x2n, to use my 2n notation here, then the pth moment of the Rademacher sum can be bounded above and below by the little L2 norm times some constant. So let's fast forward way ahead to 2018, where we have a nice paper written by one of my co-authors, Susanna Spector, and it's about a restricted Kinshin inequality. And this is where I found what I found really interesting when I sat in on a talk on this result. I said, okay, what's the restricted Kinshin inequality? Well, all we're doing is we're adding in some dependency condition. Rather than having a collection of IID, Rademacher random variables, what we're going to do is we're going to assume that they sum to 0. So they're going to be weakly dependent. There's going to be a slight dependency among my Rademacher random variables. So that means exactly half of them are going to have a value of -1, and I'm going to randomly assign the other half to have a value of +1. Like, isn't this just a two-sample permutation test? And that was the basis for the beginning of this work. So now comes to the part of the presentation where I'm going to show you 5 theorems in our paper in quick succession, and I think they're really cool. I want to highlight all of them. We don't have time to go into any of the proofs, so let's begin. If we're working with univariate data and we just want to do a 2-sample test for equality of means, well, what we can do is we can use this restricted Kinshin inequality to get a bound on the tail probabilities. And what we see here is a sub-Gaussian bound in terms of some value kappa. And kappa is going to relate to the imbalance in my sample sizes. So let's say we have 2 samples of functional data and we want to compare their means. Well, now we're not in the univariate setting and Kinshin's inequality won't help us. But the Kahan Kinshin inequality will. So the Kahan Kinshin inequality extends Kinshin's inequality into a more general Banach space setting. And what we can do is we can use the tricks from Spectre 2018 to add in weak dependencies that were not present in the original Kahan Kinshin inequality. And then, tweaking it a little bit further, we can adapt this, getting a bound on the tail probability for a 2-sample permutation test working inside a commutative LP space. What we get is that we get a sub-Gaussian bound on the tail probabilities here with a variance term based on the sample covariant operator using the Q-Schotten norm. But what if we wanted to work with those covariance operators we talked about at the beginning? Well, the covariance operator lives in a slightly different setting. It lives in a non-commutative Banach space. So what we can do is we can take Kahan Kinshin inequality, add that weak dependence restriction on it, massage it into a statistical tool for bounding tail probabilities in the non-commutative Banach space setting, thanks to the work of PCA and Xu in 2003 and their work on non-commutative LP spaces. So this leads to a very similar looking theorem, but again, a little bit different in the sense of how the variance term shows up. So now the variance term here is going to be in terms of the maximum over 2 different Q-Schotten norms. So now we're going to talk very briefly about extending our ideas from 2-sample test to K-sample test. Well, there are different ways to do this in a permutation test. If you pick up any of the following books, say on permutation testing, and there are some many good ones out there, they'll tell you that there are different ways to do this. But perhaps the favorite way to do that, if the sample sizes are balanced, that is, if I have the same number of observations in each of my K samples, is to do a synchronized permutation test. And what the synchronized permutation test does is I consider all K-choose-2 pairings of my samples, and I apply the same permutations to each of them. They can be extended to general Banach space settings through an L2 direct product of K-choose-2 Banach spaces. So the first thing we're going to do is we're going to write down this large matrix X, and X is going to be the matrix of pairwise comparisons. And then we can write our test statistic as a L2 norm. When we write this down, what we actually have is a degree 2 homogeneous Rademacher chaos. We just go right back to one of the original sources, a 1987 paper by Quapian, which looks at a decoupling inequality. And we can use this decoupling inequality combined with what we learned about Kinshin's inequality and the Kahan inequality, combined with our tail bounds from the Chernoff-Markov style of bounding tail probabilities. And we can cram it all together in this proof that sadly will not be featured in this video to get a nice theorem. Apart from the original Kinshin inequality, we don't have optimal constants in the Kahan case. And when we also use these decoupling inequalities from Quapian, we get some pretty terrible constants that enter into this. And what these constants do is they kill the statistical power. And that's disappointing. But it did lead to some really cool additional work on something that we're calling the beta or the empirical beta transformation. So let's go see what that is. First, we have a proposition that extends our theorem for univariate data. And what it says is that if I want to look at the probability that my tail bound is less than some u, We actually have a bound on the bound in terms of a beta distribution. And in the univariate setting, I can explicitly compute the parameters for the beta distribution based on kappa, which is the imbalance in my sample size. What happens in more complex settings? Now we have to pull out some heavy machinery and use Talleyrand's concentration inequality from this famous paper from 1996 that has been refined by many different authors since then. And by applying Talleyrand's concentration inequality, what we can do is get a general way to control the distribution of the bound in the null hypothesis setting in terms of the incomplete beta function. I don't know what the parameters for the beta distribution are, so instead what we do is we use this theorem as a guideline to then estimate those parameters for the beta distribution using the method of moments. And that leads to the following algorithm, which effectively says do a very small permutation test under the null setting and use those p-values generated to then estimate get the method of moments estimators for the beta distribution, shove them into the incomplete beta function, and then get better bounds. If you're interested in knowing more, there are a couple sources you can check out. Mainly, there's the article, which is currently under review, but it is posted as a preprint to arXiv, so please go check that out. Beyond that, if you'd like to hear me speak some more, you can go to the Asymptotic Geometric Analysis seminar. I will be speaking on September 5th, that is Saturday, Labor Day weekend, and I will be giving an hour-long presentation. Lastly, if you want to hear me talk even more, you can come and check out my new YouTube channel, Kashlak Stats. So in summary, what do we have? Well, we have a way of using these powerful tools from functional analysis, the Kahan and Kinshin inequalities, under various dependency conditions to do statistical testing. We can apply our methods to curves, that is, we can work in commutative LP spaces. We can also apply our method to covariances, that is, work in non-commutative LP spaces. So with that, I'd like to say thank you so much for watching, and let me know what you think. Leave a comment or just contact me. I'm always happy to talk about this some more. Thank you.